Hi there, this is a first look in Year 12 at vectors. Now obviously vectors were a topic that we saw at GCSE. We're definitely going to extend that, and we also have seen a bit of vectors when we looked at transformation of graphs. But this extends it and uses it in different ways that we've not really used them for. There's a bit of overlap with GCSE vectors though. So perhaps have a look at this. So this is a starter which kind of relates to a lot of the stuff that we're doing in vectors, and also obviously a review of stuff you did at GCSE. So pause the video, see if you can answer these, and I'll put the answers up in a bit. So hopefully you have paused the video and you've got some answers. Find the length of these lines. Now these are just really coordinates, but it matters for what we are about to do. This is stuff that we've done relatively frequently recently. -2, -4 is over there-ish. 4, 5 is over there-ish. I suppose really what we're doing is the length of the line in between them. There's A, there's B, and I want to find AB. So usually you just write AB equals. And effectively you can use a bit of Pythagoras, or you can use a rule that you might have remember from coordinate geometry. And you take one away from the other, and you get these are 6 apart, basically, in this direction. So we do 6 squared. Up and down, it's 5 minus that -4, which is 9 apart. Doesn't look like it, but my dodgy picture. And basically we use Pythagoras, and we square them and square root the answer. No idea what that is, so it says correct as 3 sig figs. So doing it now, I get the square root of 117, which is, according to me, 10.8. Doesn't say unit, so 10.8 is the answer. Write down the coordinates of the point 4 minus 1 after it's been translated by the vector -2, 4. Now this basically means 2 left and 4 up. So I reckon the coordinate becomes 2. I go 2 left and 4 up, I reckon 3. I reckon that's quite an easy answer. Find the angle in a triangle. Well, this is SOHCAHTOA, and you might remember doing this is the opposite angle, and this is the adjacent angle. Adjacent side, sorry, opposite side and adjacent side, and this is the hypotenuse. And when you do SOHCAHTOA on this, I'll write SOHCAHTOA, you'll notice the one with the opposite and adjacent is always the tangent. So I should really be doing tan theta equals 15 over 28. I'm going to make sure your calculator's in degrees. I don't think mine is actually. Shift setup, angle, and then degree, number 1. So I do the inverse tan of 15 divided by 28, close bracket, and I get theta equals to 28.2 degrees to the nearest 3 significant figures. Now it says work out cos 49, turn my calculator off, so they were. Cos 49, I get 0.656. Wants how many decimal places? Wants 5 decimal places. 656.06. And do sine 49 as well. Okay, I'll do that. 0.75471. And then hence write down this plus this. Well, notice it says squared. This basically means I've got to type into my calculator 0.65606 squared plus 0.75471 squared. And I think I know the answer. It should be 1, give or take a couple of decimal places. Here's my answers. Yes, this relies on a rule for cos and sine, which links them, and when you square them and add them, you always get 1. So I kind of cheated on that one. The other ones, I think, I've got a slightly different answer. I've got a 1 there. You check that for me. Everything else, 10.8, 2.3, and 28.2. I don't know why I've got the 0 there. 28.2. Everything else is wrong. A little notation on vectors then. Let's get down to vectors. We are going to use 2 new ways of writing vectors, and they are based on what we call unit vectors. And you'll notice down here that the I unit vector basically goes from the origin and it goes straight across, but of length 1. And because it's of length 1, we call it a unit vector. All vectors of length 1 are called unit vectors. And it goes 1 straight across, and it's just written I equals and in vector notation, of course, 1 straight across and nothing up, 1 naught. Notice, please, this can and often is written as I with a line underneath it. You'll probably get used to the fact that vectors are usually written with lines underneath, although school textbooks and exams very often don't put the line underneath. So I got into a habit now of not bothering unless I remember. This J vector is the one that goes not 1 across but 1 up. So this is also a unit vector. And again, sometimes written J with a line underneath it, but you'll notice it's now 0, 1. They are unit vectors, and it allows us to draw other vectors. So for instance, this one here I'm going to draw here is 3 across. Now allowing for a very dodgy picture, I reckon 3 across and 2 up would be something like that. That, I think, goes 3 across, allowing for rather dodgy scale, and 2 up. And you'll notice that this vector, which I'm going to call V with a line underneath, or without a line underneath, you can sometimes just put it in bold, and that's what the exam does, could easily be written, as I say, as 3, 2, but it could also be written in this new version as 3i plus 2j. And notice I'm in habit of putting these lines underneath, but you'll probably get away without them, so I wouldn't worry about them too much. So 3i plus 2j. And all vectors effectively can be written in this new version of how many across, how many up, which we've seen before. But rather than write them in this brackety form, we can write them as so many I and so many j. Now you might think, why bother doing that? And it's fair enough, because if you don't like doing it, you can just carry on writing column vectors. No one's going to lose you marks, but you've got to expect that the questions may well talk about i's and j's. So you certainly need to be aware of them, even if you choose not to use them in your answer. So this is a classic example. Find the magnitude of a vector, which is v equals 3i minus 4j. Now, unless you know what 3i and 4j are, you're not going to understand it. Notice, by the way, from here, from this starting point, it goes 3 across, and because it's minus 4, it goes 4 down. That seems obvious. And there's my vector there. And I want this length. Now, magnitude, look at this. This is a right-angled triangle. Really, all I do to find the length of this, and I should show you the notation, you usually put a line either side of it. So the magnitude of v, the length of v, if you like, is the square root of 3 squared plus 4 squared. And that should be one that you know. It's a Pythagorean triple. If you do it, that's 16. 9 plus 16 is 25, and then the square root of 25 is obviously 5. It's a 3, 4, 5 triangle. That's why I've picked it. So notice that you can find the length of a vector, and the length of a vector is called the magnitude. We need to know this name. Make sure your notes reflect what this name is. The magnitude can be written just as a v sometimes, or with this line around it, or with this line underneath it as well. So get used to the fact that it can be written in a variety of different ways. They might just call it the magnitude. And that confirms what I already said. Angles, very much like what we were just doing. So I've got a equals minus 2, 5. So let's draw it first of all. A is 2 left because it's minus 2, and then 5 down. That's my vector, which I'm going to call A. And it says find its magnitude. So straight away I can go, magnitude of A is the square root. We just did this. Notice I don't care about a negative number even, because if I square it, it's going to become positive. So I personally never even write that. It's 2 squared plus 5 squared. That's not very nice, but it's root 29. Okay. Find the angle it makes with the direction. The angle it makes with the direction of I. Well, I is going across. So I'll just put a theta there. And therefore, notice by the way, whenever you find these angles, we always are told the adjacent and the opposite. So it will always be theta equals, a bit like that start I gave you, the inverse tan of the opposite of the adjacent of 5 over 2. So I'm just going to do that. The inverse tan of 5 divided by 2 close bracket equals 68.2 degrees. Give all my answers to 3 significant figures, unless they tell me otherwise. That's what I'm going to do. And what's it asked? The direction it makes with the positive x-axis. Ah, right. Now, that's the positive x-axis. So what we do, we go around in a clockwise direction. Oh, sorry, an anti-clockwise direction. There you go, wrong there. It's very common to measure angles in that anti-clockwise direction, starting from this positive x-axis. Now obviously that's 180 degrees. We've just found this is 68 degrees. So I'm going to describe the direction. Now theoretically I could do it either way. So I'm going to say 180 plus that 68 equals 248.2 degrees anti-clockwise, but I suppose I could have done it clockwise instead. It'd be interesting to see what I've done as my answers. Let's try and do the same thing for B. So B is 3 and minus 2, so I'll just draw it over here. 3 across and 2 down. So it's like something like that. So put some numbers on it, 3 and 2. Find its magnitude, well this is B, so the magnitude of B is the square root of 3 squared plus 2 squared. Well, 3 squared is 9 plus 2 squared is 4, that's root 13. Notice I'm not trying to work either of those out as decimals. But next part said find the angle it makes with the positive x-axis. Well, that's that angle here again, theta. So theta equals the inverse tan of the opposite over the hypotenuse, over the adjacent, of 2/3. 2/3 on this. So the inverse tan of 2 divided by 3 is 33.7 degrees. And what's the direction? The direction it makes the positive x-axis. Well, again, really, I think I should do that angle, because I said it should always be anti-clockwise. So I think it should be effectively 360 minus that 33.7. So 360 minus my answer, and I've got 326.3. Again, anti-clockwise. Let's see what my answers are. Oh, interesting, I gave that as a minus. You are allowed to do that. And 68.2. And again, I've given this as a anti-clockwise, a clockwise one. So I've kind of given them slightly different to mine. But mine, as long as I describe mine properly as anti-clockwise, then that's fine. Anything else I think is right. Checking if a vector is a unit vector. A unit vector has to, of course, have a magnitude of 1. So it is this. So let's just find the magnitude of this. Magnitude of this is, well, do 1 squared plus 2 squared, ignoring the negatives. And that gives me, if I do it, root 5. Now root 5 is not equal to 1, so this is not a unit vector. It has to be equal to 1. Now look, the next one looks a bit more contrived. It looks as if someone's made it up to make it work. So let's do the magnitude of B. I'm expecting this to work. It's 1 over root 3 squared plus the square root of 2/3 squared. And don't forget you square root the answer. So it's the square root of, now that's, if I square the top and square the bottom, I get a third. This is a square root, which is square, which is cancels each other out. That's 1/3 plus 2/3, which is 3/3, which is 1, which when I square root it is 1. So yes, this one is a unit vector. Only B is a unit vector. Yes, I agree with that. Find an unknown value. Sometimes these work better backwards. So find the value of C, which makes this a unit vector. Well, I do the same thing. I say the magnitude of this is, notice it's an i's and j's. It's perhaps better if I wrote that 3c minus 6c, because i's and j's sometimes confuse people. So anyway, I square it, which is 9c squared. I square this one, that's 36c squared. I square root it. That gives me the square root of 45c squared, and that's got to equal 1. I square root that, moves it over. That's 45c squared is still 1 when I square it. C squared is a 45th. And C is the square root of a 45th, which I'm sure can be written in a slightly better way, yes, but there it is. Look, we're not going to finish all of this, so we'll do, well, there's only one more question as it turned out. We'll do that one question at the start of the next lesson, Make sure you've got good notes, and I'll see you and we'll practice this in lesson.